Hello, my name is Mustafa Melih. Welcome to Lab 101. I'm going to continue with the statistics. We're going to do t-tests. And how are you going to do t-test? What's a t-test? When would you use it? When wouldn't you lose it? So let's see which variables that you need. You would need one independent variable and one dependent variable. Your independent variable should be categorical and your dependent variable should be numerical. And you would have two groups in independent variable. So let's see with this examples. So the temperature change of two materials. You have two materials. This means this is a nominal, so a categorical data, and this influences this one. So this is independent categorical, and temperature change. It's generally continuous. So numerical data. Then this is the dependent numerical data. And you have two groups in independent variable. You have two materials in the temperature change. So this is an appropriate time to apply the t-test. And let's see the second example: rate of change of two metals. These are not metals, these are salts, but it's okay. Assume that you're doing rubidium and potassium. You're measuring the time difference. You probably wouldn't be able to measure those, but some other metals, assume those. You're measuring the rate of change, maybe rate of rusting in outside. I don't know how would you measure that. Maybe calorimeter, maybe not. So you would have two metals. These are two groups in independent variables, and these are categorical as well. Rate of change, since there is a change, and you would say the dependent variable is numerical as well. So since you're finding rate, you're subtracting one number from another, and there is numbers, that means it's numerical. Effects of different wires on resistance. I'm assuming that you're measuring resistance with a numerical value as your dependent, and effects of different wires. So you have probably two wires. You need to have two wires or two thicknesses of wire. It doesn't matter. You have two thicknesses of the same wire or the two different wires, and you would measure the resistance. That would give you you would need to do, in this case, a t-test. And how two different foods affects the release of oxygen when added catalase. Two different foods, amount of oxygen released, so you would do t-test as well. Types of t-test. Let's see. Related samples and unrelated samples. I also talked about related. Paired. It can be named paired samples. It can be named dependent samples. It doesn't matter. This when you see related, when should you do related samples, when should you do unrelated samples. So related samples is affected by time, and unrelated samples is not affected by time. So when you're measuring things, the time, if the time is influential, you would do related samples, and if the time is not influential, you would do unrelated samples or unpaired, whatever you want to name it. Let's see the assumptions for the related samples. Assumptions: normal distribution, okay, random sampling, and no outliers. For unrelated samples, you would also have equal variances. I will explain this in the Excel sheet. And how would you calculate these? How would you decide if to do non-parametric or parametric ones? Let's see the non-parametric versions of these. Wilcoxon signed ranks you would do for dependent samples, paired samples. For independent samples, you would do man with new. Let's see our examples. Dependent samples. Before I do anything, I just look at my data. What is it? What are the dependent variables? What are the independent variables? Let's write related samples so we wouldn't get confused. Related samples. Related samples. And this is unrelated. Oh, wow. Related samples. I did it wrong. Related samples, and do this one. Independent samples. Unrelated. Related samples. Let's see our data. The time is influential since there's a time change, as you can see, and we're measuring the cooling of two materials. You wrap these in like two types of stuff. You wrap it with metal, you wrap it with cotton. The cooling rate is a lot higher in this one, and for this one you would have a higher rate, a lower rate for this one. Yeah, and let's see for this related samples what we do. Related samples, the assumptions normally distributed. I come to my statistics calculator. I come to test of normality, Kolmogorov. I'm going to place my data here. For convenience sake, I put the data like this. No, not like that. Copy here, and bam, I select here. I'm not taking the time. It doesn't matter as long as the time is intervals. So the change between the values is the same. So it increases by 5. You would want to take measurements with same interval. So you would do you can calculate this test. I take my data here. In this in this site, you would have to delete the spaces. Like you had, if you had spaces like this, you would have to delete them. And if you had space, oh no, not like that. If you had spaces like that, when I selected data, I see the spaces, so I delete them so that I can conduct my analysis. Let's see, calculate p. So p is this. I take the p value. I can move this here so that it wouldn't mess with me. P value is this, A value is that, 0.05, not that one. It's fine. So we did the normality test for normal distribution. If the data is normal distributed, we see if the P is below 0.05, if the P is is above 0.05, let's remember that part. If your P value, find value, it gave it here, P value here. If your P value is bigger than alpha, you accept null hypothesis. If it's lower than it, you reject null hypothesis and accept alternative hypothesis. In this case, our P is larger than A, alpha, so we accept the null hypothesis, and the null hypothesis is the data is normally distributed. So yes, we have our first assumption here. Random sampling. So as I talked in my previous lessons, random sampling is used when you're working in social sciences. In natural sciences, it's generally similar. So you have a population in your hand, like 80 million people. You want to have random sampling so that you have as much as variation, and your values would be applicable for the whole population. If you just pick from one village, you wouldn't get like significant results for that you can refer to the whole population. But in natural sciences, we wouldn't have these problems, since generally we wouldn't have these problems if you're working with people, a population, or significant stuff. You would need to consider this. But in natural sciences, we generally don't need this, such as when I measure Pascal's pressure, it's generally it is the same all over the world, and there's no population, so we're not generally worried about this part. Or all copper wires are generally the same. Like you're talking for all copper wires, not just one brand or something. If you're talking for one brand, you need probably other brands measurements as well. So this generally random sampling doesn't affect you. There are really few cases that it affects you. And let's see if our data set have outliers or not. So I come to descriptive statistics and percentile calculator. I place my data right here. Bam, here. Clear the spaces, and let's see the percentiles. Percentiles for Q1. For Q1, I take the 25th percentile. Nice. And I take this one. Is my Q3. 25th percentile. Let's see. Interquartile range is Q3 minus Q1. And I use this to find the upper and lower limits. Let's see. Q1 minus interquartile range multiplied by 1.5. And let's say upper limit. Upper limit Q3 plus interquartile range multiplied by 1.5. This is the upper limit. Let's see if I did it right. Yes, I did it right. For finding lower limit, you would subtract the interquartile range multiplied by 1.5, and you would add for the upper limit to Q3. So be careful that you do the right thing. And let's see. This is the lower limit. This is the upper limit. If we have any value that is larger than this, we will remove it. If we have a lower limit, a value lower than this, we would remove it as well. Let's see. If we have an outlier and we have an outlier, let's see. 30 is an outlier. I remove it. Anything lower than 32, 32. No. Anything larger than 67, 67? No. Yeah. The problem with this site is that it doesn't do the calculation. This test, you cannot do the calculation without any value here. So I would suggest that you take the average of this part and directly take this average here so that it wouldn't influence your results. So this test is done by comparing the means, and if the means are not different and like standard deviation is not different, it's not influenced by this one. So you would have significant results. You wouldn't want to do this anytime, but I mean, when you have no choice in this site, if it was SPSS, we could have done this, but unfortunately, we have to do it. It's not integral, but we have no choice. You can do if you don't want to do this, you can just leave it here, and you can just leave it there, maybe if you want that. And you can reject, like if you're not meeting the assumptions, so you can do you can do the Wilcoxon signed ranks test. It's up to you. It's the same stuff that I'm going to show. Let me show you Wilcoxon. Here, Wilcoxon rank test. You would put your data here, like treatment 1, treatment 2. You select this. It's supposed to take two. It's generally two-tailed, so you can leave it two-tailed, and you can calculate here. But I'm going to show the alternative version. If you have like one data you want to do like this, if you want, you can do this. I'm showing you the two ways that you can do it. I take here. I take my values here, and let's see, where is it? T-test t-test calculator for dependent means. Let's see, treatment 1. I take my treatment 1 here, take my treatment 2 here, place them 0.05, as I said, two-tailed, calculate and P is 0.06, so the result is significant. Let's see, there's no such significant difference between the means of the groups, so P is smaller than alpha, so we reject the null hypothesis here for t-test and accept H1. There is a statistically significant difference between the means of the groups, so we prove that the test is significant. If you don't want to do this, as I told you, you can leave it there and you can do Wilcoxon. But this test is more reliable than the other one. It's up to you. You can do them both. I delete my values here and I go to unrelated samples. Let's see. No, wait. I can draw like the graphs of these if you want. When you're representing these type of graphs, you would want to do a line graph for these two. Let's see if I can do it right. Yes. So how do I do it? I explain it. I select my data, all my data like this, and then I press Control, select these two boxes, and then I click Insert, come to line graph, come to Insert, come to line graph. This will, you shouldn't do this one, especially this is like frequency type of stack line, so this shows frequency, and you should do this one line, and yeah. This shows your chart. This shows like the distribution and how it is changing. You find the when you're like writing your conclusion, you have to have your graph so that you can like talk about it. Let me explain. You find there's a significant difference between the two, yes, but which one have a higher rate and which one has a lower rate, you cannot tell with the statistical test. You need a graph. So I see my graph, bam. Let's see, cotton had a lower rate of cooling, had a high rate of cooling. So metal is significantly worse at preserving heat than cotton, I can say. I can make this comment by looking at this graph and saying that, showing my hypothesis here. Yes, this was it. We can now study unrelated samples. So let's see what is our data is about. Copper wire, aluminum wire, these are the resistance values. So continuous variable, dependent variable, and two groups. My independent variable is categorical, and we have two groups, so we're going to do t-test, and we have around eight measurements, nine measurements. Yeah, nine measurements. We have nine measurements. These are nine trials, nine separate trials. So, and these are resistance values. Let's see the assumptions for the unrelated samples. Normally distributed. Let's do the same stuff that I did for the unrelated samples. So for the related samples, I stack them like this. Bam. I come to my calculators. And where is it? Cormagnos, test of normality. I select my data. If there are any spaces, I delete it. I'll calculate. P is larger than 0.05, so normally distributed. I told you if the P is smaller than 0.05, you accept H1, H1. If it's larger than it, you accept H0 null hypothesis. The data, so our data, since P is like this, you accept null hypothesis. Our first assumption is met. I told you about random sampling, no outliers. Let's find outliers. I take my data again. I come to descriptive statistics and percentile calculator. Paste it here. Let's see if there is any spaces. There's no spaces. Percentile. Bam. I take it. Q1, Q3, Q3. Calculate interquartile range minus this one. Lower limit. Let's calculate the lower limit. Q1 minus interquartile range multiplied by 1.5. This gives the lower limit. Let's see the upper limit. Q3 plus interquartile range, where is it? Multiplied by 1.5. Let's see. If we have a value below 0.22, no, we don't. Do we have a value over 1.92? We don't have. So our third assumption is also met. Let's see if we have equal variances. So sigma squared. This is the notation, I think. Yeah, this is the notation of variance, and sigma itself is variance Uh, this was, I always forget this one. I'll write it when I remember it. Equal variances. So let's take my data here. Let's see if we have equal variances calculators. Levin's test of homogeneity. Sample 1, sample 2. Let's see. I take my samples. Bam. My samples. Bam. Place it here. I calculate it. P-value is here. I take it. I know my alpha 0.05. It's not, and that's a null. That's not the point. T-test, Levin's test hypothesis I see here. If it is larger than alpha, so I accept null hypothesis. There is no difference in variation. So our fourth assumption is also met. We can do our test here. Take them. No, I don't take like this. Calculators and t-test calculator for independence means. Come to take me to calculator. Treatment 1, treatment 2, one-tailed, two-tailed. I say to select two-tailed. Select here. Decrease. Select them. Treatment 2. If we have any spaces, I delete them. Yes, nice. And calculated p-value. Let's see p. P is lower than this value, so it's really significant. And let's see, p is a lot lower than alpha. I reject null hypothesis. There is a statistically significant difference between the means of the groups. Yes, and let's see how would I draw the graphic of this. I take the average of these two. These are the average values. I should write them away so that it's not confusing. These are the average values. I do standard deviation, but you should do sampling. You generally don't work with populations. You should do sampling. I choose that. Nice. I'm going to make and bar graph regarding these. I select these my means, my wires. Select. I'll show you how did I select those multiple times. So I select these two like this. I don't press anything. I press Control button. I don't know what's the button for it in MacBook. I press Control button. I select these two and then Insert and then bar graph here. So I come to it. I also need to add the standard deviations that I found. So let's see. Error bars, more options. I come to more options here. Error bar, more option. I come to like data, the lowest as I can go with this nibbly thing here. Specify value. I delete one here. Specify these two value. Delete two here. Get these two. Okay. So our graph also showed that the result is significant. You would ask how, why did you say that? I don't know anything that you're saying. So let me explain. The error bars do not touch each other in this sense. So if the bars do not touch each other, we say that the result is significant. We also found the result is significant here. And the reason that I made this graph shows that aluminum wire is have large resistance compared to copper wire, and we found it via t-test, or you can say it with the error bars here. This was the last part of my video. Thank you for listening. Have a nice day.